not affecting us. Otherwise, we can't use the Zoom to record the lecture. But we're happy to have that. So just a gentle reminder, this is a second to last class we have teaching. So the next Wednesday will be our very last class that we'll go over the past year papers. So this will be the last time we're teaching here. The next week we'll be going over the past year papers and also Q&A. So that means that please pay attention because we are approaching the end. Make sure that you're going to understand the material. Although I said what you will learn in the regression is very important, but I also said regression will be learned if you study the 2021, the subsequent class of the successor of this class. And that means that even if you don't have a firm grasp of everything, then you will be getting the review at that moment, well, if you ever take. But at least it means that it's good to understand what's going on because it will really help you in the road ahead. Okay. So let's click into the business. So regression and just to remind you what we're covering, because we will be we probably finish up to the R square or almost finish the whole thing. Okay, I mean, not sure we can finish it, but I'm pretty sure on Friday we will get it done. But we are. So the idea of the regression is to build a relationship between two variables, right? Numeric variable, right? So income, education, advertising, sales, and drug dose and recovery time. So they are meaningful numbers. Okay, they are numeric numbers, not categorical number or nominal. Okay, not ordinal. They are all numbers. And well, the projector is not working for some reason. Okay, it's working. So it's just like how we different from ANOVA. Right? ANOVA, the main goal is to say whether group means are different, right? Or the means are different by group. And it doesn't tell you the model, right? It doesn't build the model, except that, I mean, if they're different, then if I tell you the group mean, then you will just give me the group mean instead of the overall mean, right? Suppose you do ANOVA about, say, different groups, say the GPA by, say, college in CHK, right? So if you do ANOVA, figure out that, okay, you reject the null, and that means that if you pick up a random person, if you want to guess the GPA of him, you will, instead of giving me the overall CHK average GPA, you get a GPA within the college, right? That would be the way to explain. But you didn't go beyond saying the group mean is that is the model you have, right? But now, if you have regression, is you have a very interesting model, right? In ANOVA, it just basically tell you, okay, you have a data, but you collapse to the group means, right? So instead of that is the model you have. But now, if you have regression, the model become a little bit more elaborate, right? Because you would the model would collapse into two numbers, right? It's easier than ANOVA, right? ANOVA we have many means, right? You collapse the data into many group means if you there's a model you build. So now you're building a model that try to say and how X and Y related, and they are described by the intercept and slope. Okay. And here, just to remind you, this is a simple linear regression, so we just focus on X1, Y1. So every observation have two observations, okay, two measurement, and you try to relate them. And then we learn the way to do with those statistics is to minimize the vertical distance because you want to use X to explain Y, okay? Not the other way around. If you want to use Y to explain X, then you'll be horizontal distance. Or you don't really care about what explain what, then probably perpendicular distance would work. But we're focusing on use X to determine that, right? Just to remind you, right? This is, if you later you will see this guy. Today we talk about this guy, minimizing this guy. This actually later we will refer to is called the SSE, sum of square error, okay, which will be later you will see it play a very important role in the later aspect. But and also this is you see this is also the numerator. Okay, when you care about the standard error of regression, right? That would be the one you divide by n-2, right? This is a very important thing. Okay, but your regression is try to minimize the sum of the vertical square the distance between data and the model you're going to draw. Okay, the line. Okay, so that would be the thing when you minimize sum of square the vertical distance, the red and blue. Because square you don't care about whether the point is above or below. So that is a difference, right? So potentially you can do more stuff, right? Maybe you care about you underestimate and overestimate, right? So you can put different weights, right? Above can be square, below can be cubic term, right? If you worry about underestimate. So, but you would not have a nice property as we claim, right? If you don't use the square term, you use say cubic, you use a quadratic, or use any non-quadratic function, right? Can work, but it will not have the nice property that we want to have. Okay, so that's why we focus on the vertical distance. Okay, and in this model, we notice if we minimize the vertical square distance, sum of, and will be this formula, right? And this formula again is coming from calculus. If you ever learn calculus, this will be the thing. If you haven't learned it, then it's very difficult to understand how it's being derived. But we can understand intuitively what they are, right? At least you know, to minimize the sum of the square distance, you have to pass through the center of data, which is x bar, y bar. And also the b will be calculated as a fraction, which the numerator is covariance, the numerator variance. And we explained already why this is true, and then by the idea this should be the case, and also if they are positively related, I mean they have positive covariance, covariance coefficient, then you should expect the slope to be positive, right? If you have a covariance 0, right, then you should expect a horizontal line being drawn, right? Similarly, if you're negative covariance, you expect the slope will be negative, right? And similarly, if your variance double, then the b will be flattened up, right? So will be the line will be more flat, right? Similarly, if you double the x, it should half the y, right? And then also if you increase y a bit, then you basically don't change anything. You see if the intercept a, right? So that would be something you expect to see, right? And that, of course, it just basically justifying why this is correct. But I have told you also shown how you prove it in the technical slide. You just basically involve calculus. Okay, if you ever go to study the math department, the basic class of calculus, and you will be covered in the first class of multivariate calculus, which not the first class of calculus, maybe second class of calculus. You do that. It's not. It's not covered in the undergraduate calculus. If you do M2, do M2, do you do multivariate calculus? I don't think you do multivariate. You do single variable calculus. So if you do a second class of calculus, you will do multivariate calculus. But I guess unless you are into math, then I guess you can just safely ignore it, because I don't think anyone doing the calculus when we run the data, right? So here, just try to explain the regression, how you can get these coefficients, right? Using the Excel table or the table you drawn, and then how you derive that. And I told you, you never work on it, right? You always use Excel function slope and intercept to get the numbers. And but in optional assignment, I ask you try to do it. Okay, I'll release the solution for the optional assignment during the weekend. You have time to try to do it. If you don't, then it doesn't really matter. Just check it out how you work on that. But the optional assignment is focused on computation, which is not the main focus of our class. So that's why I make it optional. But we're asking for applications. How we do it. Okay. And so this is the multivariate calculus, how you do it, but we just skip it. So here is trying to understand statistical property, okay, of regression. And so far, we're just using calculus, right? There's no statistics at all. But we know from the second half of our course, we know that when you plot the data, it must involve random variable because the way you're sampling it, right, you can get everyone. So the error term can be coming from sampling error, or basically you talk to everyone. Everyone is have some data that you can't capture everything, right? So suppose individual Y and X, right? Then there's something that you can't measure, right? So that's X cannot fully explain Y. So there will be some random element that trying to do the Y, right? If you ever actually learn the finance, right? This is the basically CAPM model, right? It's the return of the individual stock, which is Y, right? Can be explained by the market return, which is X, right? And there also, of course, there will be the systemic risk coming to beta, right? But also there's a idiosyncratic risk, right? The stock specific risk, which is epsilon, right? So that means that you try to explain the individual stock return by the market return, but also there's some thing that is unexplained. It's a residual, right? So this is something you also learn in finance class. If you do FIN, I think few years ago, right? This finance investment class, there's a famous capital assets pricing model there, right? So that it's something that you will actually learn it, right? And the beta represent how risky the assets is, right? So the higher the beta, you will demand have a different risk attitude, right? But so epsilon will be the thing that coming from either thing you can't measure or due to the sampling issues because it depends on who you draw to, right? And then the combine of this get you the epsilon. And then in this model, we assume that x uh, are not random. So the only thing the random is epsilon, and because epsilon is random, then yi is also random. Okay, and do remind yourself that assumption one is very important, right? In order to say you run the regression, you have to assume underlying model you're running is actually linear. Okay, if the underlying y and x are not really linearly, then you run the regression will be wrong. Again, of course, you may ask what happened if this is wrong. Okay, and the short answer is doesn't really that matter because as long as you think about in the real world is a linear approximation, that's still the best fit for that, right? If you learn any multivariate calculus, that you learn any continuous function can be approximated by any polynomial, right? And then if you focus on a linear approximation, then this is you fit well well. So of course, you if you don't like this, you think is the world is more like nonlinear, then you would fit a nonlinear regression, which will be the focus of the successor class of this one, right? 202, 2021. They'll talk about that. Okay. And we have to make assumption on what we can't measure, right? Because that is a random variable. There's a focus, right? There's a statistics. So 3 and 4 tell you how this thing that you can't really measure related, right? It must be mean zero, which means that it can't really affect the relation between x and y, which is basically the on average they're gone, right? And they have constant variance and different observation, the unobserved information, right? The factor cannot be correlated, okay? And 3 and 4 can be relaxed without too much stuff, okay? But they still have used to spend many years to learn it, and that actually people who study how to relax those actually get Nobel prizes, okay? And people study this, talk about how to handle the time series, how to handle the panel data, and these are things that you actually study when you actually work on data. Okay? So that is very important. So under the 4 assumptions there, then the thing that you would try to minimize the vertical distance actually the best. Okay, it's a good, it's unbiased. Okay, the first one unbiased is good. Of course, it also means this is also have a nice property of consistency as well under certain assumption you want to make, and also it's efficient. Okay, so that's a very nice property that you want to have. Okay, and so that's why the classical regression is always work very well. Okay, under the assumption that the four assumptions you're going to accept. Okay. So the model we have, we get is the A and B, and you have to know how to interpret A and B, right? A would be the one that, what is the value of y on average if x is equal to 0, and B will be what is the average increase in the average y if x increased by 1, right? Because you assume the error term is gone, right? So that is the model you have. And the next part is the one new thing we introduce into the statistical model is you have the error term, and error term has a constant variance sigma square. And that is the part that is additional to the original model. This is the another parameter you introduced. This is and in order to measure that, we learned in the last class, the way to do is to capture based on what we call the residual, which is the estimated line you guess and the data you have, the vertical distance. And you calculate the square sum of that and n minus 2, right? This is actually when you really run the regression, you're actually minimizing this guy, right? If you remember, this is the one that you're actually minimizing, right? This is the goal, right? Remember, this is the one that you're minimizing in your regression. So this one will actually the S square or the square root version of that called standard error estimate or standard error regression. It's the thing that you try to tell people how good is your regression, right? Because if this is big, then it means that in your regression, the thing that you haven't measured is very big variance. So it means that you would have a not so much trust on your regression, right? So if you have the sigma square is very small, then your regression is very great. Okay, of course, this is one way to handle it. And I probably mentioned also if you look at many machine learning approach, okay, they would trying to figure out how to minimize this guy. Okay, this guy is our objective very often. Okay, so that would be sometimes they would call this mean square error MSE. So you later see this guy refer to MSE. Okay, because this is the numerator is S sum of square error SSE. You will notice that the whole thing is called MSE. Okay, and very often you will see people refer this to root mean square. Okay, it's a root because the square root. Root mean square error. So if you learn machine learning, then you will be seeing that there are many ways the machine, or the algorithm, trying to minimize this based on your model. Okay, and of course, machine learning need not use linear model. Can be any nonlinear. Can be any, say, what we call regression tree, random forest. A lot of those stuff you can take a look if you are interested in. But in my class, we just focus on the simplest case, right? Regression, right? And if you ever go to the machine learning class, which is I think 4,000 or 5,000, 4,000 classes, the first thing you learn is regression. Okay, so basically you can go home, write your CV, you can say you know machine learning, right? Because regression is the first thing you learn in the regression. Okay, because machine learning involves what is learning. What's learning in the machine learning here is, I can tell you a little bit quickly, is in this model we have only a y and x, right? You can imagine the model have many x, right? Y can be explained by many things, right? What machine learning is, because you have too many x in a very big data, the machine tries to learn which one are relevant, okay, to predict Y, right? And essentially, actually, that's what happened in the large language model, right? It's just like you want to predict what is the next word, right? But there are potentially many words you can say, right? The machine tell you which one to pick up to predict, okay? So more or less like this style, right? But of course, the real one is very super complicated, and there's a lot of bells and whistles into it. But that's why you can easily say from this class you learn the thing then can be extend very long way. Okay, even go to the machine learning or AI. All the thing is starting from here. Okay, so that's why we have to focus on. We have to still talk about regression. Okay, even though many of you will not continue the journey in statistics, probably this last course in your life that talk about statistics, right? But I hope I give you the meaning why we still have to go through this, because once you know it, then you know if you really want to pick up in the future, that will not be too much different from what we learned today. Okay, will be just more math, more complicated, but the idea is there. Okay, and here we have the how to calculate the standard error estimate, right? Using the formula there. I'm not going to repeat, but you know the S, right, can become from Excel. It's called STEXY, right? I think we showed you last time already how to calculate that, right? So that would be done. Okay. So I don't see there's a hopefully that's not too difficult at this moment, right? And then this is how we do the calculation. Okay. Is that okay so far? Okay, I think I review enough. Is it anything that you would have some concern, or is it okay? Or if you don't believe me, and we can show you, this is the quickly show it Excel again, right? Because uh, for those of you who let me show you again the Excel, because I guess that's rather important to know how to operate in Excel, right? So this is let me copy this information. So let me do again the slope and intercept and the standard error estimate, okay, or standard error regression, because I think this is important. A and the B and the S. So basically, this is the intercept slope. So we have this, and then how we can this formula is A, B, and S, right? So the formula of intercept is intercept. This is how you get the intercept, and the next is a slope. Okay, it's just a slope. Okay, and just bunch of y and bunch of x. Okay, and the standard error estimate will be STEXY. This is how you get A, B, and S. Okay, and these are all quick formulas, right? So probably I want to do the add in again, because I really want to make sure that you know what we are doing from now on. Okay. Let me save this file first, in case you don't know what would happen. So I want to show you the table that actually is the main focus actually for this regression topic, right? Because it's try to, same as ANOVA, we actually want you to understand how to look at the software output result, because it's the only thing you would actually do in your real world. So those Excel options and add in, we go to the data analytics. Go. If you use Mac, there will be something similar, but if you don't know how to do it, ask the AI, probably tell you how you can add on the data analysis package. So here you slow the regression here, get regression. And here is I have the input bunch of range of Y, okay? And I told the range of X here, okay? And then I would, I don't have maybe I should have from A1 to A1 to AX, because I have the label, okay? And here have the label there, and then that's done, okay? Once I'm done, then I just need to point out where I could output the information, and I just put whatever you like, just I put it here. Okay. And this is a table that I would do. Then this is the table that we'll discuss in detail today. Okay. Later you will see we will talk about this number. Okay. This we'll show it probably after the break. I mean at the end of our class. This R square is any number between 0 and 1. Okay. And this number is called the how much the model is good at. Okay. If it's 1, then the regression will be a perfect fit. And 0, the regression is rubbish. So somewhere between 0 and 1. Okay. So this is how good the regression is. And remember, S, right, is also the measure, but R square is better. Later you will see because it's always been 0 and 1. So we talk about this at the end of this class, R square. And the main thing here is ANOVA. We talk about this this class. Probably should be there at the end today, or if not, next on Friday. But the main thing is here you can see we have a coefficient. So this is a number that we just show you how to do that, right? And the S is actually here, standard error. It's this guy. Okay. So we have this yellow part we know, this yellow part we know, observation 5 we know already. So this is the intercept yellow. Okay. You wonder what is going on for this column E, F, G, H, I, J, K. This will be the focus of this class. So basically, our class is trying to make sense of this Excel output. Okay. Or if you don't like this Excel output, you go to Python or other, they will also see the similar output as well. So basically, we try to let you understand what's going on here, why we need to read this output, how to understand this output. Okay. And this is the most important thing. So we are now going to go to the business of this column. Okay. We have to understand. Good. And we will go about this 2 column before the break. Okay? This 2 column break. Okay. The key, is that a question? The key here is to understand is, okay, if you remember the focus of this second half semester are 2 things. One is called estimation. The other is called hypothesis testing, right? So once we estimate model, the first thing to do will be, of course, to see whether the model number you get is meaningful. By meaningful in this context, is this number different from 0, right? If it's different, if this number is 0, basically they don't have anything, right? If this number is not different from 0, actually there's some meaning to this parameter, right? So that's why we want to check if the parameter we get, which is slope and intercept, A and B, are 0 or not, right? If they're 0, then basically the thing is useless, right? We can throw the model away, right? We don't need the model, right? Especially B is 0. The model is completely useless, right? And we often also want to check A is 0 or not, right? If A is 0, then probably the usefulness of this model will be even simpler, right? Because you just have 2 parameters, right? You want to see if the model parameter is meaningful. The first thing to check is whether A is 0 or not, okay? And A is 0 or not, then we need to come up with the variance, right? Because hypothesis testing, we need to know how variation of this is, right? We want to see if A is actually close to 0 or not, right? And then to do so, we have to look at how variation of A is. And we can show, which is in the technical slides, the variance A will follow this formula, okay? And probably ask, okay, if I don't do math, then how can we understand this formula, right? So the first thing is you can see we can divide it into 4 different elements here, right? This is element 1, element 2, right? This is 1, 2, 3, and 4. Okay. There are 4 different things there, right? 4 items there. So I will try to explain using a graphical approach to explain why we have that. Okay. So let's draw it thing. So the first one is why the variance would make your A a little different, right? So just let me draw a graph. So remember what you're doing, okay? This is a regression model. And when you run the regression, what you're saying is, if you give me X, right, and Y are related by the alpha and beta way, linearly, right? with some error term, okay? And if this is alpha, right? And this is y equal to alpha plus. The pen is worse than my mouse. So let me use my hand. All right. So there's a line there, right? And but if I give you a particular x here, okay, in general, on average is here, right? Because that is, in this formula means in general is here. But because of the presence of the epsilon, which is what we call error or something you can't measure it, right? There's some factors not you can unable to measure, right? Just like income and education, right? Besides education, there are many things determine your income, maybe your luck, how good looking you are, how the personality you are, how your interview goes on, and what kind of people you have met, so on and so forth, right? That means that you will actually observe not this point, but otherwise you will observe some other point like this, right? And how spread out of this number can be is determined by the sigma, right? Or sigma square, right? The larger sigma square, the more likely that you would observe they are spread out more. Okay. So now with that, okay, let me compare two different situations, right? Suppose, say this is a line, right? So suppose you have the case where green dot like this, right? So you will observe this kind of data, right? It depends on where you are, right? This data will be something spread out like this, right? But remember, you don't observe all the data, right? You just observe some of the data, right? That means that when you run the regression, you maybe end up getting this data point can be this data point, this data point, right? This data point, this data point, right? So when you run the regression, you may end up, depends on what data you draw, right? Maybe end up in here, right? There's one possibility, right? Or other possibility maybe end up in here, so on and so forth, right? So, and that means that there are different A you can draw, right? Okay. So in the first case, you have A, your A is here, right? Another case, A is here, right? Because the A can be variant this way, right? So how big is it as variance of A, right? And you can see, immediately see, right? If you have the sigma square has bigger, right? The variance A is bigger, right? Very trivial. And it also show you the second case if you have bigger N, the variance A is smaller, right? If you're bigger N, that means you collect more data, right? The line you draw will be more stable, right? So the more N you have, right? Do you have more point? Then you will have less thing to do. Maybe I just draw two different cases to convince you this is a case, because without that, then you would just think I just talk a little bit too much, right? So this is the case, right? Let me draw two comparison cases, right? So this the line, regression line, but you never see this, but consider the case where you have small variance, okay? Okay. Compare the other case, you have many big variance here. Okay. Okay. So that means that when you run the regression, you are likely to observe either this, maybe this line, maybe I saw color, right? Maybe you will see this line, you will see this line, you will see this. That's the only thing you can do, right? But this one, it can be somewhat like here, can be something like here, right? Depend on the data you draw on, right? So you will see this, right? And this you compare, right? So if you have larger variance, right? You have a larger possible intercept you can get, right? And similarly, you can have the same conclusion. So this is sigma square larger, right? You just maybe just use this diagram, this increase, maybe this is easier to see, right? So if you increase sigma, then you will see this variance of A goes up, right? And Similarly, you can draw the same diagram here. I just try to draw quickly to save time. So you have two lines there, right? Again, you have same underlying regress. The model you have, right, is how what we call the data generation process was underlying data you see, right? Suppose you have one case, you have a large n with small n, right? So the case here is the data same, right? The data same, okay? The data same, okay? And the data is the same variance, okay? The data, same data, okay? Now, why increase n will become more stable, right? So suppose you have the regression, right? Based on, if you are lucky, you get this 2 point, okay? That means that your regression line will be somewhere like this, right? Somewhere like this, right? And you're unlucky as well, your underline, you just, these two number, right? When you try to fit the regression line, it looks like this. Something like this, right? Maybe I choose other color because otherwise you can't properly see it clearly. So if your data is getting this guy and this guy, right? So your point will be somewhere like this, right? So the variance is like this, okay? But now if you have to get, say, 3 numbers, right? So you can end up in like this and this, but you have to pick up some other number, right? Somewhere here, right? Then your line is much flat, okay? And the case of the orange case, like you have to some extreme point, but you would end up in picking something as well, right? So the line you drawn would be somewhere, cannot be that extreme, right? So if you have, that means that when your n goes up, right, this n goes up, we draw more data point, then the variation of the slope will be smaller, right? So that means that the more the data, right, of course, you get more accuracy. Actually, even without thinking, you would expect this happen, right? If you n goes very large, right, getting more and more data, then your variation of the intercept should be go to 0, right? The first one will be saying that if originally unobserved factor getting more important, right, more variation of data you get, of course, you would have much variation in the intercept, right? So lastly, there are 2 more factors we want to look at, right? So these are 2 cases, okay? And I have the line here and here, okay? So imagine there's a regression, your data is here, okay? In the contrast, your data is here. Maybe I should keep the maybe your point is here, maybe keep the center, maybe better. Okay. And the other case is something like this. Maybe I show this case first. Sorry. You're here, okay? As compared to the case you're here. Okay. And the difference between these two is like x are larger, right? The same variance. So difference between the two will be just you are increasing this guy, right? The number 3 data. Then try to draw this line regression. You may end up regression like this, right? Maybe you get this, right? So this is the but when you draw this, right, depends on the line you draw. It can be like this, right? And it can be like that as well, right? So the difference here is small, but when you extend back to 0, you magnify, right? So the data further away from 0, of course, the variance is larger, right? Because n is more difference. When you walk very far away, right? Then you will magnify. So that's why when data is far away from zero, right? Then you would have a much bigger difference in the intercept. Okay. Where last one will be this picture. Right. So the line is here. Okay. And you compare these cases, which you have here, 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 here. So you have 6 data point here. Okay. You also have data point here, but now with this, you can tell me which one have bigger variation in the slope, right? Compare these two. I would say if a larger variance, the second case on the right-hand side is smaller. Why? Look at the picture, okay? Suppose I pick to this extreme case, right, which is this, okay? What do you get? The line will be somewhere like this, right? Okay. And if you have another case, okay, your data is this one, another extreme case, right? Your regression will be somewhere like that, right? Somewhere like that, right? Okay. So now your data is more spread out. Okay. What will you see? Okay. Suppose the data more spread out like this. What you see? Your line will be somewhat like that. Okay. Somewhat like that. And for the other extreme case here, okay, your line will be what? Your line will be somewhere like here. Okay. So what do you see is if you increase the variance, actually the intercept, actually the variation gets smaller. Right. So that's why that is in the denominator, right? So that is exactly why I explained here when you go this way, right? That actually this guy, right, actually increase, but the variation, the intercept actually drops. Okay. So that explains the model. Okay. Now let me is that okay? Is that okay? Okay. Let me quickly talk about this and the break. Okay. So once we know this variance, okay, we're not done yet. Okay, but the easiest thing is once we're done, then we still have to look at what is the distribution of A, right? Because we would want to do hypothesis testing, right? So if you are willing to assume the error are normal, which is okay to be fine because of central limit theorem, because when things are not important, add up together is a bell curve, then A will be bell curve, okay? And once A the bell curve is normal, then we know how to do hypothesis testing, right? Because this is a what we know this is a normal, we know how to test this. This is just a set test, right? If you know sigma, right? Just A will be following in this way. A is here, right? We know this is alpha, right? And we know this is the shape, right? If we are trying to say whether C whether this is 0 or not, right? We just look at 5% add up on both sides, right? 2.5%, and see whether the number you get, the A you get, is this belong to the pink region or not, right? And only troublesome is you don't know sigma square, then you just replace by the S, right? Once you replace S, then you can use the T distribution. Okay, so this is exactly what I'm going to do in the example here, right? So the regression is a regression model. I want to test whether alpha is 0 or not, right? So what we're going to do is standard, it's a T table, right? The only complication, which is different from you learn, is n minus 2, okay? So once I know the alpha, I can test this sigma, the standard error, and this guy. Okay, and this standard error, which come from this equation, calculate that. Standard A is what? It's actually in the Excel. Okay, this standard A. Okay, let me show you where is this guy. It's actually this guy. This guy. Okay, and that complicated formula gives you this number. Okay, remember what this number? This number tells you that what is the standard deviation of this intercept A, SA. Right? This is SA. Okay, and then the T will be just the number you get was T in this here. Sorry, I'll give the break now. Okay, so this one come from this divided by this, right? Column D is divided. Column E gives you F, right? And this is the T statistics trying to see whether the A is 0 or not, right? And we know in general it's more than 2 or less than 2 will be the thing you accept or reject, but exact number we have to calculate, right? The p-value is the same as I said, right? The p-value. If less than 5%, then it's different from 0. But in this case, it's not. Okay, we'll talk about this again after the break. And then let's a break of 15 minutes as usual. So that's a break of 15 minutes. Now let me go to you reply. Okay, we'll continue talk more about the Excel table. Don't worry about that if you don't fully follow, because we'll continue talk about that. Okay, but just give you an idea what we're doing. Okay, so let's a break of 15 minutes. We'll resume at 11:38. discovery 好多方法。Exactly what you want。我幫你講出個 no， 你睇你問啦 ，N 係10分啦，你唔識我得啦，你照抄嘅啫。咪照抄啫，即係理解嘅。如果佢有啲其他部分，我覺得可能啲不啦，上啲先係跟住個男仔都要 rest 坐喺度等佢 back， 因為 back 度咧，不過中學都等，中學嗰邊等。OK， 佢於是咧就 to the right 即係你我係最我嘥錢食。咩啊？你有咩嚟？但我應該會分俾你。有嘅，真係我真係成日都翻住時間㗎啦。咁我應該睇翻晒。唔係，因為有啲係難數，所以我Excel唔出。因為我其實係定我係畫啲有前人買俾我咗。但我呢個數就我需要着咗。同埋我都係我呢個全部實寫字，我一本都有2、3，但係我要填嘢跟住一個問嘢，你都全寫字都冇嘢俾我做。你追佢嗰啲少啲經愛情，好報情人嘅啲嚟識佢，講樣嘢嚟。好報情你打，你寫開啲男嘅處理你應該你貼近佢嘅呢個係啊呢個，嗰個唔係我寫嘅，他寫嘅上家寫嘅。呢個冇乜嘢嘅，即係你講呢個嗰樣嘢，但係仲有一個叫目標。有新嘅乜嘢？係啊，講到因為你呢度係有啲咁廢，不過係調查。例如話，我今日甚至3個廢到3分3分啲3個呢個喺裏邊。我都係知道嘅，我呢條線喺度嘅，呢度行過嚟。星期冇醫生。所以我呢個你哋呢度咧攞唔到，係啊，講得係啦。呢個喺呢個星期呢個。少少辣啊！後邊咧有一台咧，佢係淨係為咗對數字光嚟㗎。覺得係冇咗啊嘛！佢一個寫第一個。3個大約接，我如果做1咪就啊！我呢個唔係，呢個係的。咁你睇到嘅，我係題最後如果話表象，你喺度睇嘅，人哋喺度會寫我。佢哋連嗰個中心會做。跟住人哋搞3方面多咧，先相將讀法嘅啦，呢個呢個一個左右。我其實唔記得數乜字數嘅咯。哦，10+10都得可以。你哋有冇可能啊？你哋邊啲嚟？我係有講曬嘅。先唔係有咩嘅？係啊。即係 So let's see how well you're doing. Good morning, or where to upload the project. Did I write that down there? I didn't. Yeah. Let me put it there. So let me check out what is our deadline for upload. Is I think will be the 29th, right? So it will be Saturday, right? So you have 2 days to refine. So let me put it there. Assignment. Knife. And allow multiple unlimited attempt again. Okay, so you can submit your project here. Okay. Why degree freedom is n-2? The simple answer would be because you're estimating y bar and x bar. So once you fix this, basically your data has a reduction of 2 parameter. Okay, or sorry, it would be the case that because you estimate alpha and beta. Okay, if you estimate 2 parameter, your degree freedom actually reduced by 2. If you estimate 3, you will reduce by 3. So that's why it's n-2. Okay, if I tell the slope, so or I tell the intercept, then you just estimate slope, then you n-1. Okay, so basically it just depends on how many thing you estimate. Then because once you estimate thing, then you have number of equation you get is just less reduced by the number of parameter you get. So I recommend that you don't get into this because to remain sane, but I would tell you that the reason is this. You can under tedious calculation, which I don't even bother to show you, only divide by n-2, that will give you the unbiased estimator. Okay, so that is the only reason. But how exactly? I think it's way beyond. I don't think it even explain in anything in the B school. So I just say this unbiased estimator. But of course, if you do what n-1 is n, the world know, will be very similar anyway. If n is large enough, so the bias is very small, so it doesn't really matter. But we stick on the one is unbiased. I hope I answer your question. Will the exam and course result be curved? The answer is no. It will be absolute grading for not just for my class, for every other section. I don't know whether you know, we CHK we adopt criterion-based learning. So if everyone got very good grade, then everyone got very good grade. I mean, there's no reason for me to do it. Okay, but of course, you know statistics, right? You know, there's when we have a large number of people, then usually you turn out to be some bell curve, right? So I mean, unless we're exceptional case, then I mean the curve actually automatically appear. Okay, not bell curve. Usually you have from my experience, all usually by module, right? You have many good students, then but you also have a student that is not so good. Okay, so likely that you have for statistics, you likely have a disproportionate people who get A and A minus, and disproportionate people get B and B minus, right? B plus is actually less than usual classes, but I'll see right how this work. But that's in general, cross section you don't see too much different because you learn statistics, right? There's some error, right? Random factor, but in general will not be too much different. And since you are here, I think under the null hypothesis, which I have from my main experience, the Bayesian updating, usually you are here, usually you would get B plus or above if you attend classes, okay, bit above. For those who don't, then will be B and B minus, and that is the thing. I mean, I think I have 95% confidence. You have you here, then most of you actually getting B plus, but I don't know. I mean, if you don't do anything exam, you don't take the exam, then, or you don't do the project, then I can't say if your project is a normal, then you should expect B plus, right? Then there's something not too surprising to see. But statistics is already like this. Either you understand, you get very good grade. If you understand, you get low grade. So that is a thing. How open book exam? Just bring whatever you can bring as long as paper. That's it. We don't chat. That's it. Okay. You can't have you can't use cell phone. You can't use your iPad. You can't use any electronic device. You can bring your calculator, but that is any calculator and any paper. That's it. I don't know what you want to do more. I mean, there's no limit on number of pages. You can bring as many as you want, but of course, it's not more the better because remember you have looked through the thing, right? So of course, open book is not something very difficult exam. So that's why I think the more thing is more like time pressure, right? It's like you have 1 hour to finish like 3 questions. So I mean,
so just 3 questions.
the 3 long question as you see the.
So not all chapters will be tested.
I don't know what you're saying. What the authors test? Look at our past paper. Do you think all things are tested? If you think so, that it's like yes. If you say is something is omitted, I don't know. I mean, I don't see. I think everything is tested, but maybe there's a limited space. I would not test every point that I'm asking, but I'm pretty sure I ask almost every chapter. I don't think I skip anything in the new exam. Yeah, I don't think the one I miss anything there. So if I ask you to find you use a p-value method, I ask a p-value explicitly, then you use Excel. Okay, Excel, you give me the Excel formula, and that is the answer you need, right? Because you really can't use Excel, right? So you just give me the Excel formula, you can do it, right? If I say F test, you don't have F table, then you tell me that based on the Excel output, how you would do the decision, right? Just tell me how you can do it, and that's it, right? But for the T, I think you have to make the decision, right? Because the T is you can either have a table or I give you a table, right? Maybe in the question, I will give you all the critical value that you need. Okay. But the F probably I can't give you everything. So actually I'm asking our TA to review the question. We're trying to make sure that even though we don't have the T table, should be able to do things. But F, we really can't do it. Probably you have to write the Excel formula. Okay. But the T is probably going to be fine. But anyway, I mean, I guess it's when alpha is too small, then it's just basically 0, right? So it's just basically you can say it's so small because remember for the p-value, unless I ask you explicitly, you just need to see whether it's less than 5%, more than 5%, right? The exact p-value is not that important, right? Rather it's 0.00001 or 0.0002, doesn't really matter because you have only 5% is the rule, or even 1%, right? If it's very small, it doesn't really matter anyway. Okay, I don't see there's a big thing that you would worry you. So much assignment due. We only have assignment you already see already, right? There's no more assignment. Okay. There's optional assignment which you may try to do it if you have fun, but we release solution so we don't have to worry that part, right? And remember, this class is 4 credit course, so I only have very few things, right? Just 5 assignment, one project, and this one open book exam. So I think my workload is not heavy compared to many class. If you look at statistics, you try to look at other school, and then I think they are much more heavier than I do. So, uh, assignment number where we guide project, I don't know, is 0 or 1. Doesn't really matter. Does it matter? If you do it, you just send. I think it doesn't matter, right? Uh, does it matter? If you like, you can put it assignment 6, right? If you really want, I think 6 is fine. I feel cold and tired. Oh yeah. So sleepy. When is makeup exam? Makeup exam will be if you have legitimate reason and we approve it, then we will do a centralized makeup exam first. If it doesn't work, then we will do individual makeup, but we will try to do the centralized makeup first. So please email your name to the TA and make sure, unless you're sickness, you have get a pre-approval, right? You have to let the TA knows and also CC me, and we keep track of who actually haven't been to the exam, and then we will organize probably next maybe December, early December, we have makeup because we will book the room to make sure that everyone took the makeup. Okay. We also need some time to make the makeup, right? So because you cannot be the same exam question because open book. So we have to make up how many people do the makeup. Extend that line. Do we need to extend? Let me ask after this and I see if I need to extend. Let's vote a little bit. So it's Wednesday. Okay, it's windy. Yeah, that's true. Intercept coefficient. Yeah, more data, smaller variance, of course. That's right. Can send on. I think TA is handling that. I think we have all the answer. Just if you really want to speed up the process, please email TA and me, CC me, to ask for the answer release. Okay, we have all the answer already, but if you don't push the TA is busy with many other things. So many things have to wait for a TA, so you have to push her a little bit. So email her and CC me, then I will just try to push. Okay. The speed is okay, except one people think is, I think, I don't know whether it's too fast or too slow. Maybe too fast. Is it too fast today? Okay. Tired? Okay. No, nah. Why lemon jump into lake? You want to be a watermelon? That's good. I missed the bus. I go to school by bus. Anyway, so let's end this one and then let's get a very quick voting on. I will get the idea of this on the light. A for the deadline. Say by let's how many day I can move because I still have to read your project, right? Not the TA, so I have to make sure that I have enough time to read your thing. So original deadline 29. I think 1 week is it enough? 1 week, I think six make it to like 6. Not really enough.
3 assignments at before 7.
I only okay, 2 more days. I mean maybe 8th, okay. It's like 10 more days, right? So I hope that is multiple choice. Yeah, no true false, right? maybe likelihood scale.
Yeah, yeah.
Likelihood scale.
大家冇咁錯，主要錯。
So agree or strongly agree, okay? Yes or you like this or like not like this, is okay? Agree or strongly disagree, okay? The current deadline is October the November 29th. So let's see this, okay? So let's vote, okay? And let me make the voting like quickly once 2 minutes, okay? And you tell me whether you want to move it, okay? We'll do it if enough people strongly agree, right? Or at least agree. If many people neutral, then I will just keep neutral. So you can tell me where 30 people voted, okay? So 32 people submit, so only have 1 minute left. Please vote. Voting is the responsibility of every citizen of this class. By the way, gentle reminder that tomorrow night our TA will do a tutorial section. So if you have any question, just please go there and have fun with the TA. Okay, or hopefully you send the email in advance if you have a lot of question so that he can answer it effectively together. Okay, you go over all the material and try to answer question. And so we have 4 people strongly disagree, and given that we have a super majority, right, more than 84, then just move to the line later. Okay, just to make sure that this is the final deadline. I'm not going to move it because I really need the time to read your thing, right? If you don't want me to read, I can do it very quickly, right? But it's not fair to you guys, right? I have to, but I have to do really, really. So you have to give me some time. I mean, I can't really just say everyone give an F, right? Or everyone get an A, right? So that's something I need to read. So give me some time to read it, right? Just move it. Let me change it in case we change it to December 8th, right? Midnight of December 8th. Okay. So it's there. So make sure that you submit. Make sure they submit, okay? And there's no excuse not to submit it, okay? Remember, you only have 1 A4 paper to do, right? Each one. So I don't see why you would be very hard pressed to do it, okay? And because I only ask you with few pages, then hopefully you do it seriously. Okay, so spend appropriate time on that. Okay, because remember, the project actually worth a lot of points, right? So just because a project in our class is like 30%, right? Not, I mean, more important than assignment, right? So most important assignment. Of course, you don't see much deviation, but there will be a big difference if you get B+ from this or A from this one, right? I think I think average grade for this project is A minus. I mean, for this particular, but it will be, if you do very poorly, then you will also get B or B minus as well. But on average, the project people will get A minus in terms of overall grading. But okay, so let us continue our journey. Okay, just to remind you what we are doing is, once we estimate the A, we want to do two things. One is called hypothesis testing. See whether A tell us whether alpha is 0 or not, right? A can tell us whether alpha is 0 or not, can test that. The second is we come up with the interval estimate for A, right? We want to see not just A, but what A can be. Okay, there are two things. Okay, and in order to do that, you have to make two assumptions. So one assumption here is you assume there's the error, the thing you didn't observe, follow the bell curve. Once you assume that, then the intercept, the A you estimate, is also a bell curve. Okay, because to know the bell curve, we can use the Z test. We know the sigma square, which usually we don't know. That's why we do the T test. Okay, we replace the sigma square by S. Okay, and this is the formula here, right? So this formula is the one that you see in Excel. This one, SA, is the one you see in Excel. So that's why we go all explicitly write down the formula. And how to do the SA, right? I already have example here. Okay, if you get data, okay, and you calculate the Y hat, right, which is how you get this, right? Because A is 3.9, right? Because A is 3.9, right? And B is 3.7, right? So we just 3.9 plus 1 times 0.7, you get this right here, right? And EI will be just this minus this, give you this guy, right? This minus this gives you this guy. So you get the two column there. And you get the square of this, get 55, right? And you can calculate the sum of the square, you get 10. You did already. S is this guy, right? So SA will be just this S over root N over this, over that guy, right? So 50 is here, right? This is SA. Okay, 2.191. And actually, this is the one that you see in the Excel file, right? 2.191, right? This is here. It's here, right? This is here. Okay. And how can you see whether this is different from 0 or not, right? Just divide, because it's a mean 0, right? So the idea is just to draw it, right? So your A is a normal, right? Center is 0, right? And you want to check, as a matter of fact, right? Is the A you found, which is 3.9, right? Is 3.9 here or here, right? And the 3.9 far away from 0, right? To judge it, you have to see what is the standard deviation for that, right? Or the variance of that. And we figure out that the standard deviation is 2, right? Using that formula, right? The standard error, what we call it. And that what we do is to divide 3.9 from 2.191 and then to give you 1.7, right? That means that it is 1.7 SD from the mean, right? Just replaced by T n minus 2, right? This is T3, right? So it's here. So this is the thing, right? And you want to say the 3.9, right? Go into this, T will be just 1.779, okay? And either you can use the critical value method or p-value method, okay? Our critical value will just give you 3.128, right? If you use critical value, right? Critical value will be using this number here, all right? This number there, right? And this critical value is 3.182, right? And this is negative, right? And 1.7, of course, is not in the region, so it's not far away from 0. So we can't say, you come to know, so we can't really say the alpha is not different from 0. Okay, so basically you don't take seriously about this intercept, right? The intercept is not something that good enough to for us to use. Okay. But at least this is the case. Or if you use the p-value method, right, then it will be t this, right, 1.779, right, 3 true, right, and 1 minus, because this is the right hand side, times 2, right, because I'm doing the two-tail test, so times 2. Okay. And so here this is the one, and the second one is confidence interval, right? Confidence interval is just you use the mean with 3.9 with A, right, plus minus the critical value of two-tail test, and this denominator, right, this is the formula, right? So we know that, right? This is how you do the confidence interval, right? It's the value plus minus, right, the critical value of the two-tail, right, and then you multiply by the standard error, right? Just how many times of the standard error, right? So that's why you will see this one actually includes 0, right? So that's why you will you can't reject the null, right? Exactly someone asked me during the break is why this confidence interval, if it includes 0, you really can't reject the null, right? This is the idea. Okay, so these two number is actually also in the Excel. So this is exactly here. The p-value is here. Let me clean up the screen, right? We have the p-value here, right? And this column H and I is exactly what we see. It's just the confidence interval, right? And last two the same thing. Okay. So that's why what I taught you is just basically how to understand this Excel table, right? Just to repeat a little bit. So 3.9 is our guess, right? And 2.19, which is the column E, is the standard deviation of the thing, right? And the column F is the t-stat, right? Which is column D over column E. And column G will be the p-value, right? If less than, we want it to be less than 5%, right? If less than 5%, we are happy. We will say this regression is really useful. And our goal is actually trying to get less, p is very, very small. Okay. And the column H and I is just telling you that, okay, our A estimate is 3.9, right? But this is only point estimate. We want to have the interval, which will be this, it can be as low as 3 and can be as high as 10. Since it includes 0, basically this is more or less useless. Is that okay? Any question? Any question before we're done? Any question? If no, we understand this field as well, we're similar. Okay, so we understand this. When we set this line, right? So this is the estimate, and this is the margin of error, right? The same thing. Okay, there's nothing new there, right? Just n minus 2 alpha over 2, right? That's the way we do the confidence interval, right? Interval estimator. Okay, so that is nothing new there. Okay. The next thing you can imagine, as we have seen in Excel, is what happened to the slope. What happened to the slope, right? With the sigma increase, we increase the slope, right? So basically, you can see here, it's just this variance of the slope, it just compared to the variance of A. Let's write that down, right? This is, you look at the variance of A, this is number 1 item, and this number 4 item, right? So number 2 and number 3 is gone, okay? The variance P doesn't affected by the sample size N. It also doesn't affected by the X, okay? So this is the idea. So let's see why this is the case. So let's check the graph, okay? Go back to here, okay? The sigma increase, you will see the slope of the left-hand side is much more restrict compared to the right-hand side, right? So increase the sigma, actually increase the slope, right? You can see much more variation on the how steep the line is, right? And similarly, you can look at the graph again here. compared to these two cases, I think you agree that the slope on the right-hand side is less than the left-hand side, right? So it's decreasing the variance, okay? So here, of course, this is understanding on the graph, but of course, the main thing you understand is by math, you have to, but we're not going to the math anyway. But that's some intuitive understanding what's going on here, okay? So the formula, okay? And if you're willing to assume that the unobserved factors are bell curve, then we have the B like this, okay? And because we know sigma, we replace by S, they call it SB, okay? This is the standard error of B, okay? And just by calculating S over this sum of square total of X, okay? So this guy is actually this guy, 0.66, okay? I can show the calculation soon, but this is the column E in my Excel file, okay? And again, once we know the beta distribution, right, then we are really ready to do hypertesting, right? This is the key thing. Testing the beta is the most important thing when you do regression, because we want to see whether the regression you got is meaningful. And beta is the key thing, right? Because you want to X to explain Y. If beta is 0, then X is useless completely, right? So the usefulness of the model is dependent on beta. So this is the key test, the t-test is the key test, okay? This is the most important test that you would have to do, okay? It's okay that the intercept is 0 or not, doesn't really matter, right? Because it's usually, we don't use the intercept that much. But the beta is the key of the model, because the beta is 0, basically you can throw all the thing away, right? Basically, the model is completely useless, okay? Because the line is flat, right? If you can't really say anything, so X is not going to help anyway. So the thing is just because you hypothesize 0, so just B minus 0 over the SB, which is Tn minus 2 degree of freedom. And also you can do the point estimate, right? And also do the interval estimate, right? So this is, we say same as what you learned from the previous topic. So interval estimate, there's nothing new here, okay? And here shows how you can do all the calculation. I guess I'm not going to involve you into the details, but just plugging in the formula. And probably I said in the class, I'm not that interested in asking you how the exact calculation, because everything is in the Excel, right? But rather, the Excel output is something I care, right? Same as ANOVA, right? I'm not interested in asking you how to calculate this directly, right? But rather, I would draw your attention on this number, right? So this is the t-stat. It's just the column D over column E give you this t-stat, right? Just basically telling you that how much your B is away from the SD, right? So it's 1.09059 away. So that is not far away enough, right? Usually you would expect at least 2 or more away, right? And that's why I give you the p-value is way less than 5%, okay? So in this particular case, this model is completely useless, okay? You can throw in the rubber spin if you run this regression. If you see this p-value is not less than 5%, so basically your boss will go and collect more data, right? If you really want the beta to be positive, non-zero, right? Of course, if the boss want to show you the beta is 0, which is also sometimes the case, then it's okay. This is a good one, right? Because if suppose this is the income and education, you figure this out, then probably you would tell your cousin or your kid, don't study, right? No point of study, right? Study don't change your income, right? If you are hired by an education institute, right? You want to show this to be positive, right? At least not negative, right? So there's some something goes on. That's a P, okay? And these two are same, right? Column H and I is the interval estimator for the B, right? For the beta, right? The beta. And B is 0.7, but it's not exact 0.7, right? Depends on variation. Our guess is actually coming from negative 0.4 and positive 2.8, right? So basically, it includes 0, right? So basically, this is also not very useful, So that is very important, how you're able to interpret this result, right? Because if you look at all the Python or R, they will give you somewhat similar. And you really need to see this, the most important thing in the model is the p-value. And once the p-value, once you know is less than 5%, then you go on looking at 95% how wary they are, right? And this is the thing that you would take into account, right? And probably you ask, okay, probably with all the information, actually column E and F is not very useful, okay? Because E and F is basically getting all the rest, right? But this is the intermediate step, okay? Because E and F is not really direct usage, right? Once you have G, then you're done, right? And also if you have H and I, then also you know how good it is, right? Already. But classically, we keep them as well. Okay, so this is how you do the calculation, right? So you have to, your hypothesis is trying to see if the slope, okay, is actually zero or not. Actually, this is saying that whether X and Y are related, right? And once you do that, you calculate the B is actually 0.7, right? And then you do all the calculation. What's the variance of B? And then you just the standard t-test, right? There's nothing new, but just single one sample t-test. Okay, nothing new, right? The only thing is need to know what's the variance. Okay, right? The variance coming from this guy. Okay, and other thing are just standard, right? You know the critical value, right? Become here. Okay, and this standard error come to here, right? So that is it. There's nothing new here. Okay, so if there are no question, then I just end here. The next class we will cover ANOVA, R square F test, and also the final thing, so that we are done. Okay, so we will be on time to finish everything on Friday. Okay, I will see you on Friday. Okay, enjoy and still beware of the weather of today and tomorrow, and then after Friday we should be warm and nice. Let me end this thing first. I want to end this.